All right, let's dive in. Today, we're going to decode a kind of secret language, the language of flow. We're talking about hydrodynamics. It's this amazing hidden set of rules that connects something as simple as the water in your glass to, believe it or not, the gas in a distant galaxy. It's this universal language, and today, we're going to learn how to speak it. So to get us started, I've got a bit of a riddle for you. What on earth could a totally normal kitchen sink possibly have in common with a massive distant star? I know, it sounds kind of crazy, right? But the answer is all wrapped up in the physics of flow, and I promise, by the time we're done here, you are absolutely going to see the connection.
Okay, so here's the game plan for today. First up, we got to start with the basics, right? What even is a fluid? Then we're going to uncover what I like to call the master key to how it all moves, and that's Bernoulli's law. After that, we'll see that law in action. Then we'll check out what happens when things get a little chaotic, when the flow breaks. And finally, we'll pull it all together and compare these two totally different sides of how fluids behave.
All right, first things first, let's tackle that first question. From a physics point of view, what exactly is a fluid? So at its core, hydrodynamics is really just the study of how fluids move. And it's all built on three absolutely fundamental ideas that, if you've taken a physics class, you've definitely heard of: the conservation of mass, momentum, and energy. It's pretty simple, actually. You can't just create or destroy this stuff out of thin air. All you can do is move it around or change what form it's in. These are like the unbreakable laws of the universe for flow.
Now, this leaves us to a really clever trick. I mean, we all know that fluids are made of just countless individual particles, right? Billions upon billions. Trying to track every single one of them, no way. That would be completely impossible. So hydrodynamics does something smart. It uses what's called the fluid approximation. Basically, we zoom way out, and instead of seeing all those little particles, we see one smooth, continuous substance. And the craziest part? This entire field of physics was developed before scientists had even agreed on whether atoms were actually real. Think about that.
Okay, so we've got our definitions down. Now it's time to meet the real star of the show. This next part, this is the central idea, the master key that unlocks pretty much everything we need to know about why fluids move the way they do.
And our hero's name is Daniel Bernoulli, a Swiss mathematician. So back in 1738, he publishes this groundbreaking book, Hydrodynamica. And in it, he lays out a principle that was just so elegant, so profound, that it's still a cornerstone of physics and engineering today. We're talking almost 300 years later. That's some serious staying power. The best way to think about Bernoulli's principle is with this simple phrase. It's the law of water energy conservation. That's really the most intuitive way to get it. So just for a second, forget about all the complicated equations. At its heart, it's just a statement about energy. You know the rule: energy can't be created or destroyed. Well, Bernoulli was the one who brilliantly applied that exact idea to flowing water. Okay, so the main idea is actually pretty straightforward. For any little bit of fluid that's moving along, its total energy always stays the same. It's constant. Think of it like an energy budget, and that budget is made up of three parts. You've got pressure energy, which is from stuff pushing on it. You've got kinetic energy, which is from its speed, and you've got potential energy from its height. So if that fluid decides to spend some of its budget on moving faster, upping its kinetic energy, it has to save somewhere else, maybe by lowering its pressure. The total amount in the budget, it never ever changes. So how does this whole energy budget idea actually play out in the real world? Well, let's put Bernoulli's principle to the test and look at the most famous trade-off of all: speed versus pressure. And a perfect way to see this in action is with a device called a venturimeter. Honestly, it's nothing fancy. It's just a pipe that gets skinny in the middle. But that one simple change makes it the perfect little laboratory for watching Bernoulli's principle do its thing. So, check this out. As the fluid flows into that narrow part of the pipe, it has to speed up, right? It's the only way for the same amount of stuff to get through. Now think back to that energy budget. If the kinetic energy, that's the velocity, goes up, then something else has to go down to keep the total budget balanced. And in this case, what goes down is the pressure. So faster flow means lower pressure. It's a direct one-for-one trade-off. And you really don't need a fancy science lab to see this. I mean, the water flowing through the pipes in your own house, speeding up and slowing down as the pipes get wider or narrower, it's all governed by this exact same principle. This relationship between speed and pressure is happening all around you. Okay, so this all works beautifully when you have nice, smooth, gradual changes, like inside a pipe, but what happens when that orderly flow gets suddenly, violently disrupted? What happens when the flow breaks? Well, what happens is something called a hydraulic jump. It's this really abrupt, almost shocking change in how the fluid is behaving. And hey, remember that kitchen sink I mentioned at the very beginning? This is it. You see this every single day. You know that thin, super fast-moving circle of water right where the faucet hits the bottom of the sink? And how it suddenly jumps and becomes a thicker, slower, messier flow? That is a hydraulic jump. Now, believe it or not, the same conservation laws are still run in the show here. But the way the energy changes is, well, it's way more chaotic. Instead of that nice, clean, orderly trade-off we saw in the pipe, here, all that high-speed kinetic energy gets violently converted into other things. A tiny bit of heat, sure, but mostly just a lot of messy, turbulent motion. You can almost picture the energy of that smooth forward motion getting shattered into a million tiny whirlpools and splashes. All right, so let's pull all this together now. Let's put these two totally different behaviors right next to each other and see how they stack up. We've got the smooth flow, and we've got the shocking one. Okay, let's do a direct comparison. In our pipe, with the Venturi effect, the change in the flow is nice and smooth, right? It's gradual. But in the hydraulic jump in the sink, it's sudden. It's abrupt. In the pipe, the velocity actually increases where it gets narrow. But in the sink, the superfast flow suddenly decreases at the jump. And here's the biggest difference: the energy. In the pipe, that energy is just neatly traded back and forth between speed and pressure. But in the jump, that clean kinetic energy gets all jumbled up, converted messily into heat, and just pure disorder. And this, right here, is the key takeaway from all of this. This is the crucial point. Even though they look like complete opposites, the exact same fundamental laws, conservation of mass, momentum, and energy, are what's governing both of them. It's incredible. These simple rules give us one single framework that can describe everything from the super orderly flow in a pipe to the chaotic mess in a sink. And that brings us right back to where we started. If these few simple laws can connect something as different as a pipe and a sink, just think about what they can tell us about the entire cosmos. That hydraulic jump in your kitchen sink? It's basically a tiny miniature version of a massive shock wave out in space. These very same rules help us understand the solar wind blasting off our sun or the gigantic jets of plasma that shoot out of distant galaxies. It's amazing, really. From your kitchen to the far reaches of the cosmos, the language of flow is everywhere.